Greetings everyone, welcome to my video on nonlinear analysis in the behavioral sciences. This video will cover the tools of nonlinear dynamical systems as an alternative to traditional statistical methods in examining complex behavior in people. Um, Traditional um, statistical methods usually view systems as linear decomposable systems. For example, if one were to do some sort of transcranial magnetic simulation to a specific part of the brain to inhibit blood flow there, and then do a reaction time test on some sort of test to measure how that component of the brain affects reaction time. Results might look like this. Without the TMS, your performance may look like the red line here, with very high average and very little variance compared to the second one, where the variance is a little wider and the mean is a little lower. Traditional statistical methods would be able to pump in these means and variances and give you a measure of the difference and whether or not the TMS had a statistically significant effect, and we would conclude that that component of the system is somehow a single component in a larger series of components and that's responsible for reaction time. But not all systems are decomposable as such. Some are far more complex. The um, the stimulation of one area might produce vastly different types of outputs than what's given input, and it might affect other parts of the system in very strong ways. These would be nonlinear systems. Nonlinear systems are typically um, analyzed from the framework of complexity science or chaotic systems. A simple example of a chaotic system would be a simple stock price change over time. This is a time series analysis of a stock over the period of 1 year. And stock prices are considered complex because of the myriad of factors that go into determining the price over time. You have thousands and thousands of people who may have been trading this stock over this period of time, each with their own psychology and their own motivating factors in trading it. Plus, you have political, geopolitical, economic factors that go into this, and that's why you get such crazy behavior. Now, there's not really much you can do with, a simple t-test or measuring the average from this to really understand what's going on here, but there are tools where we can use to glean properties from time series such as these. And just to reemphasize the lack of fit the linear methods would be in terms of analyzing one of these is we have two different time series here, x1 and x2, but they both have the same mean. It is if you were to add up all of the components over time and sum by the total, you would get the same average. However, we can clearly see qualitatively that they differ. One, the blue line, x2, is clearly in more of an ascending pattern, whereas x1 is clearly in a descending pattern. So the traditional analysis of variance and average wouldn't really do us any good in really terms of explaining what's going on with this data. So one of the tools that we're going to be analyzing in the next video is going to be recurrence quantification analysis. And recurrence quantification analysis basically analyzes how many times a system revisits a specific state that it already has been in before, how long it stays in that state, how often it visits it, different things like that. And that can tell us a lot about the system. So for instance, here we have a 220-hour long measure of wave height, and every time the wave was measured to be zero point 0.9 feet, we have a little dot here. And you can see that that occurred several times over this period of 220 hours. Now this isn't an RQA, this is not the recurrence quantification analysis. We'll get into that into the next video, which will be linked below. But you can see here, just kind of an idea, that we're going to see how often does it return to this state, and is it a something that's typically returned to? Is it a place that the system likes to be in? Um, Also, another tool that we can use, but we won't get into in this video series, but maybe in the future, is detrended fluctuation analysis. And detrended fluctuation analysis is used to analyze the system's self-similarity at different time scales. So if you look up here, you have a 1 second sample, and over here you have a 10-second sample. And you can do this for many time windows. You could do 10 seconds, you could do 1 second, you could do 10 seconds, you could do 100 seconds, and you could do 1000 seconds, and then compare them all basically. And what you're going to look for is how similar are the patterns of each four of those time windows. And that will basically tell you, give you a measure of self-similarity in that the system kind of has a built-in recurring memory system that even though it's complex and there's thousands, if not hundreds of thousands of interacting parts, that there are some behaviors that can continue to recur over and over and over again, and that there's some sort of built-in implicit feedback mechanism within the system. And this is actually determinate fluctuation analysis on some neural firing, which has been a pretty big hotbed of research in the past decade in terms of the application of nonlinear dynamical systems. So that's it for this video. The references as well as links to the next video and the final video where we'll go ahead and code up some recurrence quantification in RStudio will be linked below. And thanks for watching this video.